Okay, let's jump right in. The paper is Towards Autonomous Mathematics Research.
From Tony Feng, Tri-H Trin, and the whole team at Google DeepMind.
And the core subject is this new agent Aletheia, which is powered by their Gemini Deep Think model.
Key insight one is really the architecture. It's not like the older systems, alpha proof, that needed formal languages. Aletheia works end-to-end in natural language.
And it uses this agentic loop, right? A generator, a verifier, and a reviser to just iteratively refine proofs.
Exactly. Key insight two, performance. It's state-of-the-art. It scored 95.1% on the advanced IMO proof bench, and it's even showing real chops on PhD-level exercises.
Then you have the research milestones, which is key insight 3. This isn't just theory. We're talking actual research output.
Right, like Feng 26, a fully AI-generated paper, and Licio 26, which was a human-AI collaboration where the AI actually set the strategy.
And finally, key insight 4, they proposed this whole taxonomy, levels of autonomous mathematics to classify AI contributions, which is honestly much needed.
And that is your 1-minute summary.
Welcome back to AI Paper Podcasts. Today we're diving into that Google DeepMind paper, Towards Autonomous Mathematics Research. And this feels like a really significant pivot.
It is.
We're moving away from the math is solved headlines, right, and into the much messier reality of actual research mathematics. We're talking about Aletheia, built on the January 2026 version of Gemini Deep Think.
And that distinction you just made between math as the public sees it and research math is, it's the entire crux of the paper.
Right.
For the last few years, when we talked about AI doing math, we were almost always talking about contest math, the International Mathematical Olympiad.
Yeah, IMO, yeah.
Exactly. And contest math is incredibly hard, but it's a closed system.
Mm-hmm.
The problems are self-contained. They usually have these neat, short solutions. And, a solution exists using like high school level theorems. It's a sprint.
Whereas research math is...
It's a marathon in the dark. You don't even know if a solution exists. You often have to define the problem yourself. And the big one is you have to navigate this massive, messy body of existing literature.
Which is exactly where standard foundation models just fall apart.
Completely. They hallucinate. Their understanding of specialized topics is super shallow because of data scarcity. There just aren't enough PhD-level papers on algebraic geometry out there for a model to learn from next token prediction alone.
So let's unpack the solution DeepMind is proposing with Aletheia, because it's not just a bigger model, it's an entire agentic workflow.
Correct. They call it an agentic harness. In a normal LLM interaction, you prompt, it generates, it's a straight line. Aletheia creates a loop. First, you have the generator, which proposes a proof, or maybe just a step in a proof.
Okay.
Then that proposal goes to the verifier.
And the verifier isn't just checking for, typos or syntax errors.
Oh, no. It's checking for logical consistency. And crucially, it can distinguish between a proof that is critically flawed, where the whole logic is broken, and one that just needs minor fixes.
Okay, so if it's just a minor fix.
It passes the proof to the reviser. The reviser then patches the argument and sends it right back to the verifier. And this cycle just repeats and repeats until the verification passes or they, hit a compute limit.
That sounds an awful lot like how a human mathematician actually works. You write a draft, you read it, you find a hole in your own logic, you fix it, you read it again.
Yes. It's basically System 2 thinking, but implemented as a software architecture. And the whole thing is powered by what they call Inference-Time scaling. The paper shows this really clear log linear relationship. Meaning, if you throw more compute at the problem during the inference phase, you let the model think longer, iterate more in that loop, the accuracy just shoots up. It's not just about training size anymore. It's about thinking time.
Okay, so that's the engine. Let's talk about what it actually produced. Because unlike a lot of these papers that are just benchmark scores, this one actually generated new mathematical knowledge. They give 3 big case studies. Let's start with Feng 26.
Right, Feng 26. This is the one they classify as essentially autonomous. The topic is arithmetic geometry, specifically calculating eigenweights for arithmetic Hertzsprung proportionality.
I'm sure all our listeners are intimately familiar with Hertzsprung proportionality.
Right. Well, for those who aren't, the context is that the human authors, Feng, Yun, and Zhang, were completely stuck. They had the answer for some specific examples, but they couldn't figure out the general closed form formula. So they fed the problem to Aletheia.
And the agent just solved it.
It solved it
Yeah.
without any human intervention. But here's the really fascinating part, the way it solved it. The AI pulled in techniques from a totally different field, algebraic combinatorics. Specifically, it used Schur polynomials and the Murnaghan-Nakayama rule.
Why is that so significant?
Yeah. Because the human experts weren't even looking there. The authors admit they weren't familiar with those specific combinatorics techniques being applied in this context. The AI synthesized knowledge across two pretty disparate fields to find a path the humans had missed. That's a superhuman capability in terms of breadth.
Wow. Okay, so it's not just calculating faster, it's making connections that are further apart.
Precisely. Now you can contrast that with the second case study, LISO 26. This was a paper on bounds for multivariate independence polynomials.
Some physics and combinatorics stuff.
Right. And we usually think of AI as the junior assistant. The human sets the grand strategy and the AI does the grunt work. In LISO 26, the roles were completely reversed. Aletheia provided the high-level roadmap.
A roadmap.
Yeah, the strategic direction. It suggested using things like dual sets and log convexity. It basically said, hey, here is the path to the solution.
And the human's job was...
The humans did the grunt work. They had to write the rigorous, formal proof that actually executed the AI's vision. And the paper notes they tried this prompt on other models like GPT-5 Pro, and they all failed. Only Aletheia could see the path through the forest.
That is a wild shift in the dynamic. The AI is acting as the principal investigator.
And then there's the third case, the robust MDP's paper, ACG KMP 26. This was about complexity bounds in game theory. Here, the human mathematicians weren't stuck, they already had a proof, but Aletheia came up with a totally independent argument using Siebel's lemma from number theory.
So applying number theory to machine learning bounds.
Yes. And the AI's argument got a better bound than the original human proof. It optimized the result. So across just those three cases, you see independent discovery, strategic road mapping, and result optimization.
It really does sound like we're ready to pack it up and retire. But there's a segment 4 in this paper, and it is the reality check. They stress-tested Aletheia against the Erdős Conjectures.
And this is, for me, the most important section for anyone who's actually planning to use these tools. They took Bloom's database of about 700 open problems the community thinks are unsolved, and just let Aletheia run wild on them.
The numbers they report here are pretty sobering. They start with 700 prompts.
Right. Of those 700, the internal verifier, the AI's own check flagged 212 as potentially correct.
So the AI thinks it cracked 212 unsolved problems. That would be the greatest single day in the history of mathematics.
If it were true, yeah. But then the humans stepped in to verify those 212 solutions.
Yeah.
The number of technically correct ones dropped to 63. And here's the kicker. Only 13 of those were meaningfully correct.
13. Out of 700, that's a massive drop-off. So what happened to the ones that were technically correct but not meaningful?
Specification gaming. The model acts like a lazy student or maybe a clever lawyer. It finds a loophole in how the problem is phrased. It reinterprets the question to make it trivial, solves that trivial version, and marks it as done.
So it didn't solve the hard problem the humans intended. It solved the easy problem the grammar allowed.
Exactly. It followed the letter of the prompt, not the spirit. But there was this other issue that hints the model might be cheating in a different way. Independent rediscovery.
Meaning?
The AI solved problems that were marked open in the database, but it turns out they'd actually been solved, decades ago in some obscure paper.
So the database was just out of date.
Yeah, or incomplete. Like, there's a problem called Erdős 1089. Aletheia solved it. But the researchers dug deep, and they found this 1981 paper by Benai and Benai, and they had solved it, but they didn't realize they were solving an Erdős problem, so just never got linked in the archives.
Okay, on one hand, that's actually pretty useful. The AI is acting as a sort of super librarian, finding connections we missed.
It is useful, but it raises this specter of subconscious plagiarism. Is the model really deriving this from first principles, or did it just see that 1981 paper in its training data, memorize the logic, and is now just regurgitating it without attribution?
And that leads right into the hallucination issue, which they document so vividly with the Galambo's 1976 citation.
Oh, this is the nightmare scenario for any researcher. Aletheia gives a solution and cites a specific result from a book by Galambos published in 1976. The researchers check. The book is real. Galambos is a real mathematician. The citation is perfectly formatted.
Right.
The classical result the model claimed was in the book. It just It doesn't exist. It's a completely hallucinated fact wrapped inside a real citation.
So it's graduated from just making up paper titles. Now it's inserting fake facts into real sources.
Correct. And even when they gave the AI tool use-like access to Google search, it reduced the number of fake paper titles, sure, but it didn't stop the model from just inventing fake facts inside real papers. If you're a researcher using this, you cannot trust the citations blindly. You have to verify everything.
I want to pivot back to the tech side for a second because segment 5 of the paper is all about the engine improvements, the Gemini Deep Think model that's under the hood.
The efficiency jump here is what really makes this viable as a product. They compare the January 2026 version to the July 2025 version, the one that won gold at the IMO. The new model needs 100 times less compute to get the same score.
100x. 2 orders of magnitude in 6 months.
It's insane. It completely changes the economics. It lets them run these massive agentic loops without, bankrupting the entire lab. And that efficiency unlocks capabilities on problems the old model couldn't even touch.
They mention IMO 2025 problem 6.
Yeah, a combinatorial geometry problem. A big 2025 by 2025 grid, you're tiling squares in a specific way. The older models just failed. Aletheia solved it by constructing a macro block arrangement, but the part I found most technically impressive was the refactoring capability.
What do you mean by refactoring?
Well, Aletheia's first solution used advanced theorems like the AMGM inequality to solve it. But in the IMO, you're not allowed to cite that kind of heavy machinery. You have to use elementary proofs.
So the solution was correct, but it was inadmissible for the competition format.
Right. So the researchers just prompted it, rewrite this for an IMO competition. And it did. It successfully refactored the entire proof, stripped out the advanced math, and rewrote the logic using things like the pigeonhole principle and the Erdős Conjectures theorem.
That's huge.
Yeah.
That implies the model isn't just pattern matching text. It understands the underlying logical structure well enough to translate it from, like, PhD language to high school language without breaking the actual truth of the proof.
Exactly. It's demonstrating real semantic understanding. They saw similar stuff on IMO 2024 Problem 5, the stone game. Most human solutions you find online use these visual heuristics, happy triangles, staircase patterns, that kind of thing. Aletheia ignored all that. It derived a safe probing algorithm from first principles. It treated the grid as a state space and solved the game mechanics directly.
It wasn't just mimicking a YouTube tutorial, it was actually solving the game.
It was solving the game.
This brings us to the final contribution of the paper, and it might be the most important one for the whole community, the taxonomy. Because right now, every time an AI solves a math problem, Twitter just blows up claiming math is solved.
Ugh, the hype cycle is exhausting. So the authors propose a standard classification system to try and fix this. You should think of it like the SAE levels for self-driving cars, but for math research. It's a matrix with 2 axes, autonomy and significance.
Okay, let's break down autonomy first.
You've got level H, which is primarily human. The AI is basically a fancy calculator or a search engine. Then level C for collaboration, where both human and AI make essential contributions. That Licio 26 roadmap example is a perfect level C. And then level A is essentially autonomous, where the AI does the heavy lifting and the human just checks it and publishes it.
And then significance, because solving a homework problem autonomously is not the same as proving the Riemann hypothesis.
Not even close. So level 0 is negligible, like exercises. Level 1 is minor novelty. Level 2 is publishable research. This is where most PhD work lives. Level 3 is a major advance, something you'd see in a top 5 journal. And level 4 is a landmark breakthrough. We're talking Fermat's last theorem level stuff.
So if we apply this matrix, where does Aletheia actually sit right now?
And this is where the authors are, I think, rigorously humble. They classify their own best work, like Feng 26, as level A2.
So autonomous and publishable.
Exactly. Autonomous, publishable, but not a landmark breakthrough. They are very clear. Nothing we have seen yet is at level 3 or level 4.
That distinction is just so vital. It lets us say, this is an impressive A2 result without hyperventilating that the entire field is obsolete.
It also brings accountability. They introduced what they call HAI cards, human AI interaction cards. It's basically a log file you include with the paper. Human queried X, AI provided solution Y. It documents exactly who did what.
So we don't fall into the trap of over-crediting the AI or, the other way around, hiding the human's role in the prompt engineering.
Precisely. Transparency is the only way this whole field works going forward.
So let's wrap this up. Is Aletheia the replacement for the mathematician?
Not yet. I think the paper's conclusion is that the AI currently works best on problems that need superhuman breadth, connecting those disparate fields like combinatorics and geometry or just massive computation. But it still lacks that reliable intuition for deep, true novelty. It's great at connecting the dots, but it still struggles to invent brand new dots.
It's the ultimate research assistant, but it's not yet the lead researcher.
For now. But, an assistant that can derive proofs from first principles, reframe a strategy, and rewrite its own work to fit your constraints, that is an incredibly powerful thing to have in the lab.
Absolutely. And if you want to dive deeper, you should check the show notes. There's a link to the GitHub repo where they hosted all the raw prompts and Aletheia's full outputs. It's really worth a read to see the actual dialogue between the researchers and the agent.
It is fascinating reading.
That is all for this episode of AI Paper Podcasts. Thanks for listening. See you next time.